All right, so we are now in the last stretch of it, the home run here, if you will. I know you guys are probably getting tired of the series at this point. It's a long way to drag out a no crank scenario, but I'm doing it this way to try to show the thought process I have. It doesn't take nearly this long when you're actually doing it and you've done it consistently and you do the same thing every time. But, it brings me back to when I was first starting and watching videos like Erico from South Main Auto, Scanner Danner, DeFazio from New Level Auto, Diagnostics, a handful of them. And, I started following along with the processes, but I was always confused when I was starting out as to how they were choosing the data PIDs that they were choosing to diagnose with and how they knew what good or what bad was. Because nobody can remember every data PID on every car and every spec and every variation on it. And so I kind of wanted to drag this whole one out to show how even something that is relatively simple, or so we think, as a no crank scenario, can get complex, and how we can use the resources available to determine data PIDs we do and don't care about, what they should be, and how to use each section to go to the next logical step, and hopefully get a first-time diagnosis in a reasonable, efficient, and accurate way. So, enough of me blabbering on about that. Let's blab on about some TCM theory of operation. So the TCM determines the current operating conditions of the vehicle and controls the shifting processes for shift comfort and driving situations, receives operating data from sensors and broadcast messages from other modules. Really long, drawn-out way to say that, once again, this is a module that looks at certain operating conditions, controls shift strategies, and does that based off of a variety of direct and indirect inputs. So some are direct inputs that it then makes a decision with and buses that information as well as that decision to other modules. And some it makes decisions off of from indirect inputs, in this case bus messages, from, say, the PCM, the BCM, whatever it may be. All right. So, like I said, this is kind of where you see the words, they may not always make sense, so try to rephrase it in your head and see if it still jives. TCM uses inputs from several sensors that are directly hardwired, right? A direct input. Uses several indirect inputs that are used to control shifts. Information is used to actuate the proper solenoids in the valve body to achieve the desired gear. Cool. Pretty standard for a TCM. Nothing mind-blowing there, right? The shift lever assembly, SLA, which we will be looking at, has sensors that are monitored by the TCM to calculate shift lever position. Okay, that's fine. That's our center console shift lever. Reverse light switch, integral part of the SLA. So, hey, if we were diagnosing a no reverse problem, right now we know that reverse light switch is part of the SLA assembly. Might make it easier for you. Controls the reverse light relay control circuit. Brake transmission shift interlock solenoid and the park lockout solenoid are also controlled by the TCM. Makes sense. Really not getting into anything we care about for a no crank yet. PCM and ABS broadcast messages over the CAN bus for use by the TCM. So that's two modules that we know we're getting indirect inputs from. We've already looked through the PCM. We see good data there. We're pretty confident with that, regardless of the tune that was put into it. If you recall, we were worried about the software. TCM uses this information with other inputs to determine the transmission operating conditions. So the TCM determines momentary operating conditions, controls all shift processes, considers shift comfort in the driving situation, especially with something like an SRT8 where you have, your sport mode, race mode, all that. You're going to have softer, more aggressive, firmer shifts depending on what you're doing. TCM controls the solenoid valve by modulating shift pressures, blah, 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 blah. I mean, we can go through. We've got shift program, downshift safety, lockup clutch adaptations, all standard TCM theory. Even when I was going through this to, learn the system, I blew through a lot of this. Most of you will find if you have a good understanding of how a transmission is controlled, you don't need to read every line, and that's really what I want to get down to. TCM continuously checks for electrical problems, mechanical problems, and some hydraulic problems. All right, when a problem is sensed, TCM stores a DTC. Some of these codes cause the transmission to go into limp in or default mode. Once again, we're not super concerned about this at this point because we're not cranking, let alone starting, let alone driving. I don't care about a limp in mode at this point. Some DTCs cause permanent limp in, others cause temporary, don't care. Defaults in the current gear, once again, not useful for us, so we continue blowing through. And as we go through, if a DTC is detected, then after a key cycle, the transmission will go into limp mode, which is a mechanical second gear. Some DTCs may allow the transmission to resume normal operation, recover if the detected problem goes away. Permanent limp in will recover when the key is cycled, but if the same DTC is detected for 3 key cycles, the system will not recover. DTC must be cleared from the TCM with a scan tool. So even though that's not relevant to what we're doing at this point in our diagnosis, it is a nice little thing to keep in the back of your mind, and it may come in handy when you're diagnosing a further concern. So let's zoom back out of here, and let's go to, let's see, our TCM signals. So, TCM registers one part of the input signals by direct inputs, the other part by CAN bus. So once again, they're rehashing what we've already seen, and this is where in my critical analysis of service information class, I say things like headers and subheaders are a really good way to be able to delve into what you want to see. Generally, the beginning of any theory of operation is a paragraph or two with a real general rundown of everything, and then each one of the headers underneath it is generally structured as a more in-depth explanation of a particular section. So that's what we have here. So we already know we have direct and indirect inputs. TCM monitors the SLA for all shift lever positions, provides a low current 12-volt signal. TCM compares the on-off signals to program combinations to determine the exact position. ATF temperature sensor, and you'll see later in the video here, I misspoke. I said it's a negative temperature coefficient. It's actually a positive temperature coefficient thermistor. Measures the temperature of the trans fluid and is a direct input for the TCM, so it's hardwired in. We don't really care that the temperature can influence shift timing and shift quality. We know this. Resistance rises, the probing voltage is decreasing because of its registration. Shifting process can be optimized. Don't care about shifting, right? Now, the ATF temperature sensor is wired in series with the part neutral contact. The temperature signal is transmitted to the TCM only when the read contact of the part neutral contact is closed, because the TCM only reads ATF temperature while in any forward gear or reverse. When it is in park or neutral, the TCM will substitute the engine temperature for the ATF temperature. Cool. It's a good bit of data to know if you have shift concerns and everything else. And it is interesting here that it's wired in series with the part neutral contact, yet you will not see that on the schematic. We'll take a look at that briefly. Starter interlock. Now, I'm going to be completely honest with you. When I was going through this stuff and I'm looking at the TCM, I went with my subheaders. Like I was saying, I went through and I saw starter interlock. Perfect. That's what I care about. So the TCM monitors a contact switch wired in series with the transmission temperature sensor to determine park and neutral positions. So we're just rehashing what we already have here. TCM senses transmission temperature is high, switch supply voltage. It doesn't tell us what our switch supply voltage is, but, excuse me, it's likely going to be 12 volts or 5 volts. Pretty good guess there. confirming the switch status as open. So with a high voltage, so we'll say 5 or 12 volts, the switch is open, which means that we should be in park or neutral. TCM then broadcasts a message over the CAN bus to confirm this. PCM receives the information and allows operation of the starter circuit. So this is what we care about. This is what we really want to get into. So, I mean, we can briefly look at the other stuff here. You know, we've got, let's zoom back in for you guys. We've got some inputs here. We've got brake transmission shift interlock. We have shift schedules. Once again, we found our golden nugget of information there. Do we really need to continue going through everything? I mean, here we have a real generic setup where we're actually going through. It shows us where the TCM is. It's right under the steering column. That's nice. It's easy access, so that is useful. But this is our real generic run-through profile. Nothing groundbreaking, nothing amazing. We found our golden nugget, so do we really need to continue reading? My opinion, no. If I want to learn the system better so that I do better the next diagnosis I have, I'll make a notation in one of my notebooks that I keep. Haven't brought one of them out in a while, at least not on video. And I'll make that notation, and on my own time, lunchtime, break time, whatever, I'll go through and I'll read through more of this to learn the system better. So let's take a quick look at the TCM schematic to see why I was not even aware there was a temperature sensor wired in series with the park neutral switch and why it will matter to us. So if we look here, we have the factory schematic, and here's our electric hydraulic control unit. Here's our trans temperature sensor. Signal goes into the trans controller. And nowhere here, going between factory and aftermarket diagrams in both starting and charging, transmission control, as well as some theory of operation and all, you don't actually see a diagram in any of them, and feel free to look it up yourself. It's actually good exercise in efficiently navigating your service information, is seeing how in multiple different areas they give you different little tidbits of information as well as different diagrams at times. Can really make a huge difference in a diagnosis. But anyway, in this case, we're not actually seeing this wired or being switched in series with our transmission neutral switch. But if we go here, and here's just an internal diagram of the switch sitting down in the trans, not real useful. But right here is where we get a good bit of information. Not sure why it's not letting me zoom in here, but we'll read through it real quick. The electro-hydraulic control unit assembly of the NAG1 transmission contains a temperature sensor to monitor the transmission oil temperature. We've been through this a million times. You guys are wondering why. You'll see in a minute or two. The sensor is wired in series with the transmission park neutral switch. Okay. TCM expects to see a valid voltage level from the sensor when the shifter is in the reverse or any forward drive position. So we know it wants to see a valid voltage level, and we've already established that that is going to be below switch voltage. It's going to be a positive temperature coefficient sensor, and it's going to be below switch voltage. Switch voltage is going to be either 12 volts or 5 volts. Doesn't clarify at this point, but we know the likelihood is either 12 or 5 volts. TCM also expects to see an open circuit condition when the shifter is in the park or neutral position. So it wants to see high voltage, 5 or 12 volts, in park or neutral, and it wants to see less than 5 or 12 volts in reverse or any forward drive gear. When the controller detects an open circuit in reverse or any forward drive position, the DTC will set. So if we see our 5 or 12 volts in reverse or any forward position, we're going to set a code. Now notice it does not say that we will set a code if we see low voltage in park or neutral. It's only concerned with seeing high voltage in reverse or drive. And if you think like an engineer on this one, and this is where it comes back to critically analyzing, why would you only set a DTC for one and not the other? Well, do we really care in park or neutral what temperature the transmission is? Is it going to affect our shifting strategy? Is it going to affect our shift feel, driver comfort, overall performance, overall longevity of the vehicle and the transmission? It's not. It's in park or neutral. The trans is just sitting there doing its thing. It's not shifting. It's not being put under a load. So why would we really care if we were reading a fault in park or neutral? More importantly, technically, the only fault we could have in park or neutral is open circuit, or short circuit, or a lower than expected voltage. And what's the worst that's going to happen with a lower than expected voltage? We're reading an accurate transmission temperature. No real reason to set a fault code for that, right? Well, as you guys will see shortly, the transmission temperature sensor is the main reason, or the reason, why we have this no crank. So why they wouldn't set a plausibility code, it's up to individual preference, whoever programmed it, whatever design they thought was best. I can see why they wouldn't put a plausibility code in there, but as you'll see, once we delve into the scanner data and some meter readings, you'll see why a plausibility code would have made this 10 times easier, and in all honesty, a 5 to 10 minute diagnosis. So that's that. Let's delve into the on-car stuff. I know service info can be pretty boring, and I've rambled on long enough, so let's get to it.
So after going through our service information and going to the next step in the chain of command, in this case the transmission control module, we read up on it. We saw some interesting data, and most importantly, the starter interlock circuit, which dictated that the transmission temperature sensor / switch is wired in series with the park neutral switch. In park or neutral, it should show high voltage, in this case system voltage, of 12 volts. In our particular case, 11.7 volts. We've had the car on for a while. No battery maintainer, but we should see system or battery voltage for that particular data PID. In reverse or drive, we should see actual transmission temperature. In that park neutral with that high voltage, that system voltage, our transmission temperature will actually be a substituted value, which is gathered from the PCM and the engine coolant temperature sensor reading. So it's an interesting little bit of data, and we're going to actually delve into why we care about that. But this is take 2 of this particular section. So I'm already into the scanner. I'm already into the transmission control module, and I started highlighting data PIDs that I'm concerned with based off our interpretation of service information and what we've seen in other modules so far. So we've said it time and time again, brake pedal depressed on a remote keyless ignition system. Very important to see that brake pedal in all the modules that are involved in the starting system. Current gear we want to see. In this point, current gear should be a direct input from the transmission, not a bust or indirect input. We have an OK to crank data PID that we see here. Very concerned about that. A Prindle display request, which is going to be a direct input based off of the range sensor that is then going to communicate to our instrument cluster. Now, our instrument cluster, which I may not have noted this before, but our instrument cluster does agree with whatever gear selection we have at any given point. So we can feel pretty confident that that's reading correctly, but we have the data PID. Takes half a second to click the button. We'll monitor it. Our selector lever position, which is actually our center console shifter here, we're concerned about that. We want to make sure that's reading because it is a direct input. We're concerned about that. And we're going to scroll down to our temperature sensor voltage, which is that switch / sensor that is in series with the park neutral switch that we read about in our starter interlock circuit data. Notice how we have two data PIDs here that are transfluid temp and reverser drive only, degrees Fahrenheit, and then what appears to be a duplicate data PID of that. So, as I just said 45 seconds ago, in park or neutral, the transmission temperature is a substituted value that is taken from the engine coolant temperature sensor reading. So it is an indirect reading as well as being a substituted value. It is read directly by the powertrain control module and then sent over the CAN bus network to our transmission control module. Now that goes from an indirect to a direct input once we go into reverse or drive based off of the design of the switch. We go from that high system voltage, battery voltage, down to a negative temperature coefficient temperature sensor. I believe, I may correct myself right at the bottom of the video here, and then reads actual transmission temperature. So let's go to our graph view. And right here we see 111 and 111, which is honestly probably what the shop's at right about now because I've got all the fans shut off. Our selector lever position is in park. Temperature sensor voltage is 1.416 volts. That is nowhere near close to system voltage, so that's thrown a red flag, especially based off of the service info we just read for description of operation for this trans module. Our OK to crank is reading false. Another big red flag. Our Prindle display request, in this case that would be a direct input to the transmission, but that becomes an indirect input to the instrument cluster, is reading in park. Our brake pedal is now depressed because I've depressed it, and our current gear is park. So let's go to reverse here. Now in reverse, our selector lever position is in reverse. Obviously, we are not OK to crank. Our temperature sensor voltage has not changed. Our Prindle display request, both on the instrument cluster and within the scan tool, has gone to reverse. Brake pedal is still depressed. Our current gear is showing as neutral. Vehicle's not running, transmission's not shifting, so that makes sense. Now we're going to go to neutral. Selector lever agrees with neutral. Prindle display on both the instrument cluster and the scan tool agree with neutral. Still no OK to crank, and our temperature sensor voltage is still low based off of what it should be. Now we're going to go to drive. Once again, selector, drive is good. Prindle display, good on both the scan tool and our instrument cluster. And our current gear, as we discussed, remains in neutral. So where do we go from here? Well, we're going to pull up the schematic, and we're going to take a look, see where the easiest place to get to that temperature sensor wire is. We know we're reading a lower voltage than what we desire to read in park or neutral. Now, 99% of what I do is in a flat bay. I don't work off of a lift. A low-to-the-ground car like this means it's not easy for me to get directly to the transmission plug and test it there. So I'm going to look for what's the easiest access point. So that's what we're going to do. So the instrument, or lower dash panel here, I've already got the screws out. I've already got this set up. And what we have back here is I am actually back probed. The TCM is located directly under the steering column below this lower dash panel. And I am actually probed into a dark green orange wire, which is our transmission temperature sensor. And what we're hooked into here, and you'll see the voltage reading in a second, but what we are hooked into, is just a regular old multimeter. You will see our voltage is inverted. So I've got my positive lead to ground, I've got my negative lead to my temperature sensor. There's a reason for that, which we'll get into in a second, but ignore the negative. We have 1.4 volts, which agrees with our scan data of 1.41 volts. We have our 1.45 volts which agrees with our scan data pretty closely of our 1.41 volts. Now, why I have these hooked up backwards is part of the nature of the snap-on leads. We have this secondary ground jumper. So what I'm doing here is I'm actually using a jumper wire that will now run directly to that transmission temperature sensor, and I'm going to jump 12 volts to that using my smart bob, my breakout box here. So like I said before, our breakout box has all these banana plugs in them. This one with the big red LED on it is battery. So we're going to hook that jumper wire in, and we see we got 12 volts here. You'll also have noticed that our temperature sensor voltage went up to the full 5 volts, and our OK to crank went to the true position. We've got the 12 volts there, and I'm going to kind of wiggle myself in here to press my brake pedal. So, battery voltage fires right up. So our fault here is where? So what we actually narrowed this particular no crank down to was a failed transmission temperature sensor. One that wasn't fully failed. In fact, it was reading temperature within the range that we would expect it to, but the interlocks weren't working properly. Essentially, when it should be seeing full system voltage, it was maintaining at temperature sensor reading voltage, which was a fault within the transmission. Unfortunately, I'm not going to be the one tearing into this transmission to figure out exactly why that happened, but we've narrowed down the fault to there, and they can take it from there. The interesting thing is we look at how many different modules receive that park neutral input, something that we're very familiar with. Actually, I had a Nissan up in Staten Island a few months back, or almost a year ago, I guess, about now, that also utilized 2 park neutral switches, and they disagreed, and that created an intermittent no start, but not an intermittent no crank. In this case, we have the transmission controller, the selective lever assembly, which is our actual transmission shifter in the center console, the PCM, the BCM, and the RF hub were all seeing a park neutral status that they agreed with. The only difference was that in-series temperature switch / sensor was not going to system voltage when it was intended to in park or neutral, which would be a plausibility check within the software. So instead of looking at all the other data, the instrument cluster also agreed, because it's a bus input. Once again, we're looking back at our direct versus indirect inputs and outputs, and we need to understand those. But everything was agreeing for the most part, except for that one indicator, that one plausibility check. Now, we threw no trouble codes for that. I mean, we did throw various communication faults and things along those lines, but never once did we throw one for a transmission temperature sensor out of range. I mean, how would the car know it's out of range? It goes with the simplest programming, the easiest. In this case, it looks at the fact that despite the fact that we see, multiple park neutral inputs that all agree, I see this voltage lower than it should be, so I'm going to inhibit cranking. It's an interesting fault, one I wanted to take you guys along for a couple reasons. One, I've never seen it occur before. Like I said, I've worked on heavy equipment, medium and heavy duty trucks, automotive. I mean, I've been in all aspects of the repair industry, and I've never seen a no crank caused by a transmission temperature sensor fault before. 2, as we saw with our Pro Charger, our oil catch can, our tuned PCM, our former nitrous hookup, and the like, I know a lot of us get nervous and scared about dealing with aftermarket modifications, tuned vehicles, things along those lines. We struggle enough with factory service information, let alone bringing in all these outside details. And I can admit, I kept going mentally back. As much as I tried to divorce myself from it, I kept going mentally back to a problem within the tuning within the PCM. And what we really need to do is we need to rely on our critical thinking and our critical reading skills, our ability to think outside the box, and our ability to understand indirect and direct inputs and outputs, how they may be communicated, and kind of take all these little puzzle pieces and put them together into a big picture. Instead of getting stuck in our mind that there is a specific fault and we're trying to prove that fault, what we need to do is allow the data we collect and the information we can gather based off of service info, schematics, and what we physically read with a meter, a scan tool, a scope, temperature sensors, infrared thermometers, whatever it may be. We need to let all of those guide our decision-making process instead of our own preconceived notions, our hit databases, our fixed databases, what the guy 3 houses down said he's run into on every Dodge Charger ever. You know, we got to put the pieces together, and we got to really use all our abilities, all our senses, look at the vehicle, look at the history, look at everything to be able to do effectively and efficiently diagnose vehicles for a first-time fix. I had some fun with this. If I had to break this down, I spent a lot of time reading up on this particular vehicle on my own time. If I had to break it down into percentages, I would say 92 to 94% of this job was reading service information, navigating through service info, reading it, understanding it, making notations. I would say 2 to 4% of it would be scan data, going through scan data, seeing what agreed, what disagreed, finding data PIDs we did and didn't care about, and narrowing it down from a world of information to a manageable amount of information, and then cross-checking that against both our schematics and our service info and what we actually saw in operation. You know, we may interpret service data this way or that way and see a different interaction in real life, so that's something to keep in mind as well. And I'll say the last little bit was multimeter. I mean, we hooked into one wire, confirmed a scan data reading. We then used that same tap into the wire to run 12 volts to it to simulate a correct operation of the switch. And we had correct data PIDs in the scan tool at this point. And we had full correct operation of the starter circuit, the crank. So, kind of cool, kind of different. Something I haven't run into. I had some fun with this. I do enjoy challenges. And I learned a lot with this. Hopefully you guys did too, and if you did, hit the like button, hit that subscribe button. I'm going to try to get some more videos out to you guys. There's a very specific type of case study I like to do, and I like to make sure you guys have as much information as possible. So I can't give you an exact release schedule, but hopefully you enjoyed it, and I'll put them out as I can. Thank you, and have a good one.